Okay, I just want to get a sense. First of all, I give my apology. I gave at yesterday's talk. It's been 20 years since I've been in sort of the business of analyzing historical data. So it was really an honor for Chris to invite me. And this work was done primarily by a series of thesis students that I had. And there's lots and lots of details in their theses. I'm just going to show a few of it. And I probably won't be able to answer all the questions that you have. But I'd just like to what's associated with winning battles? If you were trying to say, hey, what are the 2 or 3 things I'm going to look for to decide who's going to win a battle? What would you choose? Any thoughts?
I would try to figure out what's the quality of the training, quality of the force.
The training advantage in the data set I'm going to look at. They have a historical assessment of training advantage.
And that's closely connected with the leadership and the whole leadership philosophy of the long process. So those two, I think, are usually very closely connected.
Yeah, but not force ratio.
Yeah, of course, that's also important because, but to a large extent, usually, if you are going to attack, do not attack if you are very, if you have less than one-on-one.
Yeah.
That you wouldn't do that. But
so if you attack,
so usually the forces will be more or less in a kind of numerical balance, whatever we call it.
If you attack less than 1-to-1, historically, how often have attackers won when they attack?
Not that often.
Okay.
Yeah. I think of asymmetries. Usually the winning side has to have the advantage of some offset, qualitative, technological, size.
Yeah.
Right. If you're the smaller force, like in the pitch I'll give today on the Battle of France, the Germans have the smaller army. They win decisively. And because they have technological and tactical innovation that gives them an asymmetric advantage.
Yeah. The one thing I'd comment is some things are objective and easy to measure. Relatively, force ratio, number of tanks, things like that. But training's a little bit, I don't know, more subjective, or certainly leadership is. Yeah. Captain Hindsight. I thought of taking that, adding that to my slides, but I was just too tired last night.
I've thrown something even more difficult to
Yeah.
measure now.
That's what I was wanting to say, and I was wondering how exactly to say it.
Yes. Well, I think the term is will to fight is the term du jour.
Yeah, it was. So I'm looking forward to reading that Rand paper. I guess it's kind of an update of Roland's.
That's a good question. I haven't read the whole thing. I think they developed their own methodology for assessing.
Yeah, it's what I'm very interested in that. I teach combat bombing class that's actually started. I've recorded a bunch of lectures, and the students have to read and present papers. And I give a set of papers, including Niles. But one of them, and I say, hey, you can suggest papers, and that paper was suggested by the students. I'm going to let them do it. Yeah.
I think what comes before morale is the quality of the leadership and the quality of the training. So morale can be created by those factors. Of course, other factors apply as well, but I think those are the 2 most important factors. And then someone talked about morale. I think it's a factor that is relevant, and it's kind of difficult to find it.
So in this data set, one of the questions would be how correlated are morale, training, and leadership, right? Momentum, other things.
Yeah, it's closely related to the training, but like the doctrine of the force and exactly how well do they fight the way they wanted to fight. Many times, like you may have a way of war you want to fight, but how well do you align to that approach?
So it's interesting. Some of those would be, particularly sort of, very different fighting styles. We saw World War II with the innovation and things. Probably don't show up in this data set. I was interested. I told Chris yesterday, of course, it's a huge task, that we heard a talk yesterday that said shock is one of the 4 sort of predictors of success. And there's no column for shock. They have surprise. I would have thought they would have been, before listening to sort of the definitions, I would have thought, well, surprise, shock, aren't those kind of the same? But he defined them differently. Yeah.
I also get your first.
Nathan.
Nathan. Nathan had a very good point. Do you have asymmetry in any kind of capability? I would say. If you have if you have a little less or a little more of a capability like artillery or sensors and so on, it doesn't matter that much. But if you have a huge difference, or you have a gap that you are missing one of those capabilities that you usually need for a combined armed flight, then you have a very these are a very big disadvantage.
Yeah. So in this model, we looked at ratios, so tank ratios, artillery ratios, combat sortie ratios. And the way we looked at them is something called partition trees. Interactions should emerge that you need this and this. Yeah. So we'll see. Okay, so let's get started. Next slide, please. Yeah, so here I start this lecture with several questions. So some questions. Next, yeah. Who tends to have higher casualty rate, attackers or defenders? I asked my military professionals, right? They're mid-level officers, and you would think they would know. That's sort of a very basic question, right?
Actually, I think it would be the winners suffer lower casualty rates than the losers, regardless of posture.
Well, so that's an interesting question too, because you usually have some choice in attack, and you wouldn't attack unless you think it would be advantageous. So, yeah.
Oh, I've cheated a little bit because I've read about this, but the interesting thing is that if there is not a breakthrough, so it's that you're winning, then the attacker and defender, if the attacker is able to push the defender back, it's almost equal.
So, and often it's, yeah, and so within a battle, there can be, if I'm initially attacking, I might be exposed and they're better defended, prepared, to take attack, to move me to a position where I can do. So there's certainly a time element to that, right?
Yeah, so it is depending on the situation. If you're able to if you're attacking and you win the first engagement, or you push the enemy out, the defender out, you'll be almost. If you're not able to kind of win, the attacker losses will be a little bit higher. If you're able to do a breakthrough, then the defender's losses will be quite much higher, and it will be catastrophic if you are another.
So one of the problems with this analysis, and it's always a question in statistics, when we looked at it, this is just very aggregated, start of battle, end of battle data. And you can lose within battle trends and patterns and stuff through that. And I also worry, if you're familiar with Simpson's paradox, when you aggregate and group, you can get patterns in the aggregated data that is the opposite in the individual. So I view this as just very exploratory, very suggestive, as opposed to concluding. That's the way I look at it. All right, next. How often do attackers win? Right? You don't usually have choice to attack. So if you win 90% of the time, 50% of the time.
They're hugely contextual, but
As all of these are, right? Every battle has unique aspects to it.
In Trevor DePuy's combat databases, the attackers tend to win about 2/3 of the time.
So, and this data set I got from CAA, which I think they got from
their CDBI is their version of.
Yeah.
Yeah.
Yeah. Next, and elsewhere. So we'll just go through what's the relationship between force ratio and victory. War force ratio is good. So I'll just ask correlation coefficient, right? Is it close to 1? Is it close to 0? Things like that. Next. Yeah, what factors are associated with winning land battles? This is all land battle type stuff. Can we predict future outcomes? So a book I really like is Dean Hartley's Predicting Combat Effects. Yeah, where he took, I think this, if not this exact same data set, something very, very close, and did a bunch of regressions to it. What we did is, in different, instead of fitting a logistic regression probability, I'll show you later, we use something called partition trees, and we'll see that in a little bit. Yeah, next, do these questions change over time? Because is it of interest just to historians, or is it of interest to modern military people? And this is sort of, setting expectations. We're looking for relationships, patterns, and trends. I don't think anything, these aren't a random sample of battles, right? So I'm not sure what population you rate them to. And so there are all sorts of statistical issues with it. On the other hand, if you see patterns again and again and again, you're just sort of building strength and evidence. Okay, next slide. Yeah, so just the context. One of the things I like about Dupuy, and he received a lot of, Trevor Dupuy's work, he received a lot of criticism from nuclear war, that war is constantly changing, right? And so that's always something to look at. Are these trends sort of constant in time? And I like this, only historical combat is real combat. If you read Roland's material, that even in the most realistic simulations we have, the physical training sites where people get hungry, tired, hard drives crash, the intensity of warfare is up to 10 times higher than it is in real battles, or for the real battles. So even the best simulations we have with real people and real equipment are systematically different than real combat. So, okay. Yeah, so I'm going to talk about the data set. I'm going to go very quickly through summary statistics, just tables of data. And then this is, I think, what will be maybe interesting and new. I haven't seen this elsewhere anyway, is predicting combat outcomes with classification and regression trees. Next slide. Yeah, so here is the database. We got it from CAA. I think specifically Bob Helmold sent it to us. If you read this news, I glanced at their theses before coming here, and they thanked him in their acknowledgments parts. But it's 660 land battles from 1600 to 1982. Parts of the analysis, some of the data is missing, and some of the analysis looked at trends within campaigns, and you needed to have enough battles within a campaign. We saw one of the talks yesterday. So some of the analysis you're going to see, and it's been so long I don't remember all the details, involved 660-ish land battles. Others might have involved 552. And there were 17 sort of logical campaign conflicts, World War II, World War I being some of the bigger ones. The database has 140 attributes. I don't know of anything even close to it, on it. And some of them are objective factors: who's the attacker, who's the defender, force ratio, tank ratio. These are the things we look at. So we have two columns divided one by the other. Primary defensive posture, etc. It also has more subjective factors. So training advantage, who had the initiative, surprise, things like that, and weather and terrain factors. And what we did is we built the model separately. So first we've said, hey, can you predict just on objective factors? And then can we do better if we throw in subjective factors, and then weather and terrain? Next slide. Yeah, so here are the 17 groupings so that you can see and get a feel for. Next slide. Yeah, so here's more detail on it. So on it, the numbers of battles in each of these time frames to look at. So this one at 657. I don't remember why it was 657. Three of them might have been removed for some reason, missing data and maybe some key elements. But the battles per period for the attackers and defenders on it, so you can see which countries were involved. Russia over time, for instance. Next slide. And I'd be happy to send these material to anybody who's interested. Yeah, so where in the world these occurred? So you can get a spatial sort of the intensity of the data set. So how many battles, 78 in 1940, 79, 78 in 1944 was the most. Just a couple other summary statistics. The defender wins, the medium force ratio was 1.31. The defender wins mean. The attacker to defender force ratio is 1.92. Attacker wins medium is 1.66. Attacker wins mean. That's where you get a few outlying data points. You can run it, and some of the standard deviations. So just some big summary statistics. Next slide. Yeah, a couple things. There are some missing data elements. It's an amazing data set, but it's not everything's filled in. There are some NAs. When we fit who wins, the data set has three outcomes: attacker, defender, and essentially a draw. We wanted to fit it to bivariate response, so we gave the tie to the defender on it. So we're arguing whether that's the right thing to do, or maybe use a more sophisticated statistical technique, or, I've always thought, there are different degrees of winning, right? I look at some of the battles there. I thought we had won Bunker Hill. You took the hill, but we gave you 3 casualties to 1. Yeah, and for subjective factors, they give a range. So, and this is like winning. It's just 1 minus 1 in the data set, 0 for a tie. But for some of the factors, assessments go from 1 to 4. So I had a huge training advantage in 3, 2, 1 qualitative assessments. Attacker advantage will be with an A. So defender advantage with a D. No advantage, you'll see a 0. Next. Yeah, so one of the things I liked about this, the Lanchester, one of the problems was the force ratios don't change that much over time, and they're correlated in how they do it. So there's, you're trying to fit, for a regression analogy, when the x's are real close together, the error and slope can be very high as they're apart. But here there was some nice ones. So force ratio, 17 to 1 was the maximum, about 1/3 was the lowest. So you got a difference of 57 times. So this data set had a real broad range of attacker defender force ratios, artillery ratios, mortar densities, things like that. So that which I think is an important thing in the time phase data, which we talked about yesterday. You had very little variation. Next slide. Yeah, so okay, who has a higher casualty rate? Go ahead. So here are the 17 different campaigns, the mean daily casualty rate percent. I think it's deaths per day. And you can see, this is one thing, we saw a version, something very similar to the shown yesterday by Chris. But over time, daily casualty rates have gone down, even though weapons have gotten much, much better. But for the most part, these are means, there are distributions around them. But at the end of the battle, start to end, that the defenders almost always have a higher daily casualty.
Are those only for the battles and actions, or do they count the operation over a longer period?
I think it's just for the battle, whatever in the data set. But I don't remember precisely.
I would note there that this particular data set is very loose in how it defines the battle. And some of them are division to division engagements, while as the entirety of Operation Rapid is considered a single battle.
Yeah, and one of the things I really liked about Dean Hartley's book, an advertisement for it, is he sliced the data in lots of different ways, trying to get at that thing that, hey, is this a pattern that holds true in the aggregate, that holds true in different time phases, things like that.
I know that the DePuy Institute has a suite of databases descended from the original CDB and augmented by research that's been done by them, and they're now aggregated by size of battle. So you might talk to Chris about maybe making use of that.
I did, but I didn't have the money to buy it. I'm going to make another run at it. Yeah.
So if we were to look at the war in Eastern Ukraine right now, which parts would be considered a battle versus just the campaign?
Yeah, you'd have to ask the people who made the database. Yeah, and that's right. I mean, that's the curse battle we talked about yesterday. I mean, it had all sorts of sub battles within that battle, but it's all aggregated. So,
Yeah, I'm curious.
tell you what DePuy how he would segment them.
17th century pitch battles, how did they decide who the attacker and who the defender? They attack the initiator. Because sometimes you've got, it's not clear which side initiates as opposed to which side is in the defensive position.
right, no, I agree. And I said, I didn't make this database, and I'm far from an expert or historian on it. I'm just a statistician looking for patterns and stuff like that. So unfortunately, I can't answer that question, but those are great questions for Chris. Yeah.
Oh, it's rough. I was when the G3 in Brigade North. We had an exercise where we played as the aggressor and we attacked into northern Sweden towards Swedes and Finnish troops. And the terrain was quite challenging because there were very few roads and only one lane roads and so on. But I said to the battalion commander of the medical battalion, I said, we are going to check now during this exercise if you have a evacuation system that holds up, that actually is good enough. So I said, okay, because it was instrumented on both sides. So I said that, okay, every second casualty we will evacuate. Of course, we had some statistics from our landwater center and kind of where
US Marines are worried about that question right now.
Yeah,
In distributed operation. Yeah.
we saw that the casualty rate, if you took 50% of them, because our understanding was that in instrumented battle, you will take more chances than in a real battle. So we cut it in half. And then we actually ended up with roughly 100 plus minus casualties a day in the brigade. And that is actually quite close to the numbers that UP gives as 100 to 150 a day for a brigade or regimental sized unit.
And you asked the question too. So this data set lumps battles in terrain like that with one in an open desert or something like that. So, you know, that's why I said we're aggregating over lots and lots of stuff. And each battle has unique sort of specific circumstances to it. Every one of them. Yeah. So, okay, next slide. Yeah, dispersion. We saw this yesterday over time. So the weapons got more effective. Troops by necessity spread out. Next slide. Yeah, so I'm just going to go through these really quickly. Just talk about them. Win of the attacker. So in the data set, unknown outcomes, -9, it said there were 2 on one where it said we didn't determine a winner. Defender wins 217, draw 43, attacker wins 98. And so this is your 2/3, right? If you don't include draws, it's 65% in this data set, 60%. And so when we're fitting models, that's sort of our default prediction. If you can't do better than 60%, you know, why use your model? This simple model could be attacker wins 60% of the time.
I have wondered about that data set, whether that outcome is a result simply of an artifact of the data, because of the data grab, or if there's something related to, because attackers have initiative and decide when to attack, that most battles are initiated by an attack.
Yeah,
I don't have the answer to that one.
and so this is one of the questions I ask my officers, and most of them think the attacker. Well, I get splits. Funny, human dynamics. I'll get things where they think, oh, of course the attacker wins, right? You don't attack unless you're in a position to do so. And others think, well, defender usually is in better positions, maybe on their home country, things like that. Next slide. So I'm going to go through a whole series of things. So force ratio and winning. Here's histograms with the 1 means this is a histogram of the force ratio in the battles where the attacker won. Here's a histogram of the force ratio in the battles where the attacker lost. You get some outliers out here. So we zoom in going from 1/4 to 1/4. And so you can see, yeah, there's more probability, more battles where the attacker won with higher force ratios. But the differences aren't stark, right? They don't, boom, jump out at you as sort of being separated. Next slide. Yeah, so I just copied this from the thesis. So God is on the side of big battalions. So total number of battles attacker wins with different force ratios. So this is a student just trying to chop down the force ratios in sort of bins. So in cases with a force ratio of 3 or more, the attacker won 68% of the time. And then from 3 to 2.5, 66, 62 from 2.5 to 2, all the way down to when it's 1.5 to 1.4, the attacker won about half the time and it stayed stable. Less than 1, there were 144 battles and the attacker won 74 where they attacked less than 1. Not a random sample, remember. So a decent number of these, if I remember correctly, is from the Arab-Israeli War. Well, yes, 11, attacker won 11 of 15 when they were outnumbered.
It feels like it naturally goes back to the idea you don't attack unless you think there's a good chance of winning. What's a good chance look like? Well, it's something 50-50 due to all the other factors beyond the force ratio.
Yeah, no, that's right. Next slide. Yeah, so here's just a plot of that and the values that they took. So notice they're not equally spaced, they're really more category. but you can see higher force ratios do better, but perhaps not as much as lots of people think on it. I mean, Chris used the term 90% if you have 3-to-1. His data set says 70%. Next slide. Yeah, here's artillery ratio, same thing. When you had advantage in artillery ratio, you won more often than when you, the winner, when you won the battle, you're more likely to have a higher artillery ratio than when you lost, but perhaps not as much as you won. And some of these are pretty severe, right? 8-to-1, I've outnumbered 8-to-1, or I had 8-to-1 and I still lost. Next slide. Yeah, close air support ratio sorties. So here's again the ratio when the attacker won all of the land battles, if you remember, and when the defender won. Next slide.
Who lost with an 8-to-1 advantage in artillery?
I don't know. That's a great question. And I should have gone in and, like us all talked yesterday, where they isolated the specific battles. And that's one of the great things that this data set is. It's not a random sample. Be careful of the lessons you learn. But whenever you find something that doesn't fit the pattern, that's interesting, right? That's yeah.
The French in 1940. The Germans substitute their artillery with close air support. The French have basically a big World War I artillery defense.
I was wondering whether what happened with the 8-to-1 advantage in artillery was offset by a 5-to-1 advantage in air.
Well, that's what the question is from the asymmetry. If you're on here, so there's so much more that could be. I mean, the statistical analysis of this data set is just sort of scratched the surface, and that's why I was surprised. When Kristen sort of invited me, that I would have thought. And I looked. I would have thought there would have been a lot more done. Yeah, tank ratio. So I probably should have done more. I just cut and paste these from the thesis for the most part, but this was, box plots might have been a better way to show it. Next slide. Yeah, so attacker tactics, defensive posture. So now these are a little bit different. Here are the postures of the defender, and win-loss for the attacker. So you can see kind of how often the different postures in this data set. And then, so delayed, the attacker won 16 out of 20 and so forth. And here's the attacker's primary tactics. So 5 broken into 5 different categories, and then whether they won or lost. And so you can see, in this data set, frontal attacks are almost always what was used.
At the level of the battle.
At the level of the battle. Yes, no, exactly. Yeah, all of this is aggregated with all of the, if you're a statistician, you really worry about aggregating data. Yeah. Next slide. Yeah, so the combination. So if you have defensive posture, tactics, you can look at how often the attacker won in the proportions on them. Next slide. Surprise. So now moving on to more subjective factors. In the data set, the attacker surprised 156 times, the defender 14, no surprise 455. And then you can look in the battles, the attacker won. They had surprise 124 times. The attacker never won where the defender had surprise, and neither one. So this looks like, and this one of the things we saw yesterday, right? This variable looks like it's going to be pretty informative. That's one of the things we think will be, if you get surprised, it gives you a much better chance of winning. Yeah, next slide. Relative air superiority advantage. So again, you can look at it where the attacker had it. This is the proportion that they won. So this looks like a pretty important. When the defender had the air advantage, the defender usually won. So like this is something that at least in the summary statistics will be meaningful. Next slide. Leadership advantage. So again, this is a subjective assessment, and I think this was a variable you would know for sure that actually went from 4 to -4, 0 being the same, +4. We aggregated it down to 1, 0, -1 on it. But yeah, so what you suggested, so in the data set, when the attacker had a leadership advantage, they won almost all the time on it. When the defender had a leadership advantage, they typically won.
There's some circularity in there, though.
Absolutely.
Somebody won, obviously he was a good leader.
This is why I was going to put the Captain Hindsight audit. So, yeah. And you'll see that later. When we look at predicting combat outcomes, the trends over time. Yeah.
Leadership is treated as part of combat effectiveness in covered models. However, person reading this data on occasion, he suggested the idea that it might be worth separating leadership into generalship and leadership. In other words, generalship for whoever the top commander is, the generalship level, representing general on staff, and then leadership representing sort of like field grade leadership.
And that's wonderful. I think this data is just so immensely valuable with all the caveats put in. I think, I was trying to get Chris to add another column for shock. And that would be another one. Good luck. But I all for it. And with all the money that DoD spends, it seems like this is just such a tiny fraction for actual combat data. So, yeah.
So just a question again about the secondary. This seems so important. I'm sure that how did they decide on leadership advantage? So I now think about Ukraine. It's a frustrating one. We just said at the level of strategic leadership, Putin, brilliant, perfect conception, perfectly executed. The other guy, comedian.
Let me move on to that because I think we all know that, right? Yeah. But you're exactly right. I'd love to talk about that afterwards. It's like, well, I think more interesting stuff when we actually break down the trees. Yeah. So, next slide. Relative combat effectiveness. And so I'll ask the question, how correlated in the data set is relative combat effectiveness to leadership? How correlated is it to training? And those are great questions, but you can see relative combat. And so one's is sort of the proportion. Most of the battles, they didn't give a relative combat effectiveness advantage. But when the attacker had it, they tended to win. When the defender had it, they tended to win. So that's a variable that should be predictive. Next.
But how in the world do you specify that metric?
Great question. Keep that in mind. And then great talk to Chris, right? I'd love to sit around and talk about it because we would just had this data sent to us by Bob Helmbold. Pardon? Yes, his books are great on that.
Yeah.
Yep. Here's the training.
It's still an open question.
Yeah, training, relative training advantage. So you can look sort of at the summary statistics here. When the attacker had it, they tended to win 80% of the time. When the defender had it, kind of 50-50. Most of the battles, neither had it. Next slide. Yeah, morale. Again, how do you define morale on it? But most battles, neither side had a morale advantage. Very few times the defender did. That by itself is interesting, I think. When the attacker had it, they tended to win over 80% of the time. Next slide. Relative logistics advantage. So I was interested that, certainly in the U.S., we pride ourselves on having just tremendous logistics support. And I was surprised. I know it's not, most of the battles aren't U.S., but I was surprised it wasn't more this. But, the 53 battles, the attacker had a logistics advantage, they won 47, and so on. I think it's more important for the attacker. Yeah. Next slide.
Got to be able to get the stuff to the battle.
Momentum.
That's more of the attacker's role.
Yeah. So, this is interesting as expected. Defender typically doesn't have momentum. So yes, that makes sense, at least to me. Attacker, and then next slide. Yeah, intelligence advantage. Again, most of them not. I would imagine it'd be interesting. So the data set stops in 82. As we've got a lot of more technology type things and communications and sensing. It'd be interesting to see it more often now. One side, certainly, I think, a lot of the data sets were pretty comparable forces on size, technology, and country. And, a lot of the wars we've been fighting recently, battles, we've had a huge technological advantage. So it'd be interesting to see what shows up. Anyway, here it is, and that's it. I'll send anybody with these slides and the data set that CA sent us. Next slide. Yeah, initiative. So attacker usually has initiative, and they win about 3/4 of the time. They have initiative. The defender rarely does, but when they do, they win every time.
I ask, do you have the definitions there? What actually makes up the advantage? How do you define that? Is that available in the
Yeah, there is. It's actually in the spreadsheet itself. Here's the variables, here's very terse definition. Yeah, and I think that they are discussed in the books too. Yeah, these books.
That's basically a who's first, right?
No, I don't remember the
and
specific
implemented.
advantage.
Actually, it looks like, I mean, I noticed that the database, Bob Humboldt said he was CDB 90G.
G, that's it.
So it's the gamma region. I think, CA has been adding some of their own definitions. I don't remember some of these categories being in the original.
So, okay.
Combat database.
Yeah, so that's, yeah, I have the CAA one, which I don't know what changes they made
I think,
from.
yeah, I think they've added some variables.
Next slide. Yeah, train effect. Let's go look at it and go quick. I mean, we could spend a lot of time, we could spend all day talking through these, right?
But that's symmetrically defined.
I don't remember.
And the database will also describe if you have, let's say you have the initiative advantage. Just also mention what kind of other advantages you have.
Well, so it'll have the whole list. So you know, when we fit models, it's probability weighting is a function of all these things.
So,
Yeah. And so their interactions should emerge, especially with these partition trees. Like, yeah, this and this, you do really, really well. Next slide. Yeah, so this, again, we could spend a long, long time on this. This is just a correlation table between winning 1, 0, -1, or 1 -1. We made those. And force ratio, tank ratio, artillery ratio, fly ratio. And so let's just go down a column because we're focused on interesting. The correlation between force ratio and winning, 0.13. So it's positive, but it's not that strong. Yeah, tank ratio, artillery ratio, fly ratio, combat effectiveness of the attacker. So that's the highest we've seen so far. Leadership. So I colored the ones that are really dominant, 0.52. Morale, intelligence, technology of the attacker. This is kind of interesting. And later on, we'll see it in a time series. A lot of the older battles, the technologies were very similar in the data set. Yeah. Training, logistics, surprise. I don't even remember what aero A, air sorties or air superiority, probably. Yeah. 0.21. Initiative. So leadership, initiative are the two that sort of stand out here. And they're all positive. We have an advantage, but these are the ones, the big one. It's also interesting to see combat effectiveness and leadership that had a 0.54, whereas training and combat effectiveness 0.68. That might be the highest in the table.
Sorry, can you just remember what FR is? Is that
Force ratio. Force ratio. Yeah. Yeah. And what I said earlier is that force ratio goes all the way from 0.3 to 17. So it's a span of 51 times. Next slide.
Sorry, if I can just interrupt a moment. Just about everything you said today is broadly consistent with what Roland said. Yeah, it's interesting to see two takes, very different takes statistically, pointing in the same area. I'd say no more than that.
And this was done when Roland did his. This is over 20 years old. Next slide. Yeah, so forecasting battle winners. Sun Tzu told us how to do it. He had 7 criteria, right? Which of the 2 sovereigns has the moral law? Which of the 2 generals has the most ability? And so on. We're going to use classification regression trees to do the same thing. And this was really motivated by Dean Hartley's book is you need sort of a reasonable level of regression to kind of understand it, what its coefficients mean and logistic regression and things like that. But classification regression trees are a non-parametric method. They're invariant to linear transforms. You can fix, they're very easy to put in both quantitative and categorical data to them, as you'll see. Professor Berkeley championed that about 30 years ago, and now they're mainstay statistics. But I never learned about them when I was getting a PhD in statistics. Next. Pardon?
Who was the champion?
I'm blanking on his name, and my good friend, he was his advisor. And if you send it to me, I will find. Send me. But Y classification trees, easy to understand. And if I had more time, I was going to redo these. The software we used was R, which is free software, but doesn't have nice graphics. I was going to use Jump and redo them, and it has nice pictures, so the pictures won't be as pretty as I would like to see, but they're easy to understand. As you'll see, they straightforwardly handle a set of predictors that contain a mix of numeric, quantitative things, qualitative, non-parametric. Tree-based models are adept at capturing non-additive behavior. So you don't have to specify the interactions or the non-linearities. Dropouts don't just emerge.
Was it Leo Bryman?
Leo Bryman, yes. Yep, exactly. Yep, Leo Bryman. Tree-based models are very, yeah, my friend who's this, I don't know if you saw NPS on Jeopardy. That one of my colleagues down the hall, my colleague for 20 years, won the first ever Jeopardy's professor tournament this year. So Sam Buttrey's his name, and he's NPS's most famous professor by far. The CNO is sending congratulations, Sam. Yeah. So next slide. So let's get to it. So the tree model's built. Next. The first one, we just looked at all the objective factors. We were just counting things. Next, model 2, we added to that the subjective things, surprise, training, leadership, etc. Next, model 3, we added train and weather factors. Next, so now we have it's a pretty big suite of predictors now, right? I can't remember, it's 30 or 40 all told on it. To do these, to see how well it works, usually you have a subset of data you train it on, and then you try and see how it predicts. So we broke it into, and I did make these, as a student did. These are 5 different subsets. These are the times. These are the battles. These are the training sets and the size. And then this is the test set where we took them and predicted. Notice we're doing a little bit of extrapolation here. So we use this to train the tree, this to test the tree. Statisticians, you're always wary about extrapolating, right? So, but that's because we were trying, the idea in mind was, can we look at the past to say something about the future? So test size, training set size, test size. And our goal is 0.6, right? We can be better than 0.6. This attacker wins 60%, we're adding something. Next slide. Yeah, so in the base model, 60% is our goal. And in here we broke it down a little bit. Some of the models were fit to all outcomes, some of them to just the clear-cut outcomes. I think that I don't know if we threw the tie goes to the defender out. I don't even remember what we did on it, or if there was something in the database that said, because who won the battle is not always obvious. Next slide. Yeah, so here is a tree. So this is objective of factors on subset 5, which is the whole data set that we use. So we're looking over a long period of time, but we have the biggest sample size. And if you just look at all the data, you see a 1 says that you should predict the attacker wins. The attacker's going to win the majority of that. And then it splits. So what a partition tree does, it looks over all variables, continuous variables, discrete, categorical variables, and looks, if I split the data, I want to get the data, in the simplest way, it's sort of regression in some squares, that I want to split the data in such a way to minimize the sum of squares in the sub nodes. And the sense you can think of, I want to split these into 2 subsets that are as homogeneous as possible, is the way you look at it. So very interesting. The first thing that splits is force ratio. That it says if the force ratio is greater than 4.060, attacker wins, and just stop right there. Yeah, it'll go down until it reaches some stopping criteria. Just stop. Then, if the force ratio is less than 4.06, you look at the primary type of attack. Is it a frontal? If it's a frontal assault, you still get attacker wins. And you'll see on the next one, if there wasn't such a big tree, you could break out how often they won within each of these nodes, how often they lost. And if the primary attack is one of the other ones, like double envelopment and stuff, the attacker wins, stop. If you get to here now, so you've gone down, this is all of the battles at this part of the tree, then it goes on force ratio again. When you see variables come in different layers in the tree, it's suggesting a nonlinearity. But so if this is true, and force ratio is less than 0.8, now the defender wins. That's the majority of those cases. And 0.8, the attacker wins. And the next one was cavalry ratio. Remember this data set aggregated together. And you work your way down. You can see when you try and rate variable importance, there are a bunch of heuristics based on the height, where they break. You know, the first branch is the single variable most important on all of it, artillery ratio, et cetera. And you can work your way down. And it's in the thesis, it's online, so you can look at it. As I said, I could talk about these, just any one of these, for a long period of time. Next slide. All right, but how did the tree do? Here's the misclassification rate, so how often the tree got it wrong in the training set. And here's how it did in the test set. And here's how it did in the test set with clear-cut outcomes. And so when we use, what's the bottom line? When we used objective factors in the different times, particularly older battles, the trees weren't very good. They didn't predict the combat outcomes very good. Maybe they're doing a little bit better. Certainly the fits are better if we're thinking of these as descriptive models. All right, next slide. Here's model 2. We have all factors. So we added to that the leadership, the supplies, things like that. And now it's a smaller tree I'm showing, so you can see that the attacker won 398, the defender won 260 in the total node. The first split is on initiative. When the attacker had the initiative, they won 336 and lost 113. So that said, this one variable explained the most. If you only have one piece of information, that's the one you would want on this. When neither side had the initiative where the defender did, then the attacker won 62 and lost 147. Then you come down to force ratio. If the force ratio is bigger than 3.68, then you come here, and then even though they didn't have the initiative, they won 23 and lost 14. Leadership down here. You look at which variables show up. And when you see one factor after another, it really suggests a nonlinearity, that there's a nonlinear relationship there. But so you can work your way down to it. Next slide, please. Yeah, adding subjective factors dramatically improves the fit. I don't remember why this was not, but now, instead of 50%, we were at 20% error rate in our test set. And so we're doing better on it. With clear-cut outcomes, if you could predict 87%, that's pretty damn good for combat. Well, that's just the best case. Next slide, please. Yeah, and so what happens over time? So what we did a test set. We varied, said, hey, if we looked at 125 battles, what's the probability? And then we're going to forecast the battle number 126. We have sort of sliding windows. So we use the last 125 battles to predict the next one, and see how we did. Yeah, trial and error was come up with 125, results in 533 predictions because we need the first 125 to get the next one. The average rates, I don't remember exactly how we did it with the sliding window and the 30. The average rates come from 30, aggregating 30 predictions, the next 30 predictions together in the sliding window. 5 battles is used. So how did important variables, misclassification rates over time? That's what we're looking at. Next slide. And here you go. 2 different things. Here's the indexed in the battle. Remember, we're grouping them in 5s. So groups of sliding windows of 5. And we did it for the index in the battle and then over time. So some periods had more. And so you can see that very early, we're doing really, really well with this classification rates less than 0.2, but that's that because it's leadership and it's the Captain Hindsight issue. I'll just leave it at that. And that's sort of interesting when new things happen, almost like World War I, World War II, maybe things have changed dramatically. And suddenly our predictions suddenly went, they're no good anymore. And then they, over time. But so this is over time how well we did in the battle. And then, by year. Next slide. Importance of variables. So this is the first split in that sliding window. So we take 125 battles, say what split first? What was that one piece of information you'd want most? So the first 200 is leadership. And actually, remember, this is the first 300 in the 325 in the data set. Over time, and you worry about that. Yeah, you're a great leader when you win. and you're not such a great leader when you lose for the most part. Then it switched to, oh yeah, I've got it right here, initiative. So leadership, then initiative. So let's think of World War I, initiative. And then, so what's interesting, is this because the historians haven't had time to catch up and make the assessments on who are the great leaders or not? But suddenly it switched to things like momentum, training, artillery, tank ratio. So it suddenly becomes, resist force ratio. I can't see, I have to line it up. But now it becomes more, at least the data set suggests more technology sort of things, more equipment stuff. Next slide. Yeah, so we looked at the relative importance of variables and we used a heuristic, a weighted thing. So you got 100 points if you were the first split in the tree. If you're the second level, you got 50 points. If you're the third level, you got 25 points, and worked our way down. And so relative importance of variables in World War II and after. So fly ratio. So one of the things about the first split is it masks all the splits below it, right? And so this one says, hey, you might have missed me. Fly ratio wasn't dominating, but it was second or third across the board. And that's important to know. So when you looked at them, no, so it's interesting, relative importance of variables in World War II and after, artillery, fly, equipment type things, leadership, didn't matter in this data set. Relative importance of variables before World War II. Remember, a lot of stuff we aggregated across. So leadership, initiative, force ratio shows up here, force ratio. Next slide. Yeah, so one of the other students looked at, is there a nationality factor, right, on it? And it came up in the discussion. I'm really running out of time. But when DOD used models to estimate Desert Storm, they way overrated the casualties. I know his faculty, friend of mine, former Army Colonel Jeff Applegate, was a captain at CAA at the time, and his analysis using SEM was going up to the National Command Authority, but pretty high up on it, which forces should be the next to arrive and then how should we do the attack, stuff like that. And of course, they way overestimated casualties, right, by over an order of magnitude. And he said, someone from Britain, and I don't even know who, I didn't catch the name or if I've long forgotten it, came in and said, well, based on historical data, your biggest problem is you're not going to be able to take enough prisoners, you know, historically fighting with the Arab nations against the West. And he ignored that because he said, I'm not going into a general and saying my first assumption is the enemy's going to surrender. And that's a little bit of the philosophy of DOD. If we could beat a 9-foot enemy, we can beat a regular enemy, right? And so, I mean, in some sense, that was the thing on it. But so nationality factor. So we did some studies on nationality factor. It's a thing, Ali Chakan. You can go take a look at it. He looked at 4 countries: Germany, Britain, USA, and Israel, to try and look at it. And so the first thing, by the way, that broke, attackers 165, 62, a smaller data set. It might have been a time frame in it. If the attacker lost, if the nation defending was Britain, Confederate States, Germany, or USA. And so I think this might have been a whole data set from some of the studies. Before World War I. So there you go. I have it here. Next slide. Yeah, World War I battles, and I'm going to go through. So the first thing, force ratio greater than 4. They won 15. Yeah, that force ratio was overwhelming, right? Yep, in World War I. That's exactly right. And so, okay, and you could, this is all online. You want to go through and read them sort of in detail. Next slide.
There's a confounding variable in there.
I don't have time for it. We got 2 minutes. I've run over. We did our discussion while we went along. World War II battles. So you can look at artillery ratio. First thing that breaks, right? Next slide. So the focus on 4 countries, how often they won. Next slide. Yeah, proportion of battles won by the attacker in different periods of time: Israeli, US, Britain, and Germany. Next slide. Yeah, force ratios of attacking countries. So when the force ratio when the attacker won, force ratio when the attacker lost. You know, the one that really stands out is Israel, right? They had smaller force ratios. And they had higher force ratios in the battles they lost. Next. Yeah, so summary, classification regression trees can do okay in the best case. I'm cherry picking 85% predicting them. But if you only use the objective factors, they didn't do so well. They were missing 30% at the best. Importance of leadership. Yeah, I'm going to add my Captain Hindsight to that right there. And it's sort of the recent emergence. Is it real, or is it just historians haven't had time to catch up on technological factors in the battle? Or are we having more asymmetric battles? That's a great question too. As I said, I view this as exploratory.